Hello, ma'am. Good afternoon. I am Godfredo Hippos Jr., and this is my output for the machine problem in Module 2 of Math 221 OL, Numerical Methods for Ordinary and Partial Differential Equations. The methods that I choose to implement are Simpsons 3/8 rule and the centered finite divided difference with the Richardson extrapolation. Since I am done discussing in Module 1, the reasons why I choose the software, which is the PyCharm and also the Python language, so I will no longer discuss it again. And for this time, I will now proceed on discussing the Simpsons 3/8 rule, or the source code of the Simpsons 3/8 rule and the CFDD with Richardson extrapolation. Okay. So this is my source code for Simpsons 3/8 rule. As you can see here, I imported libraries. These libraries are similar to the one that I used in Module 1. Now, the NumPy is used for numeric calculations. SymPy is used for symbolic mathematics, and for the tabulate is used to represent the datas in tabular form. Okay. And for this part, I declared x as my all throughout symbol, or the variable that I am going to use all throughout the code. I printed out the header or the title, Simpsons 3/8 rule. And then after that, I created a loop asking for the function. This function should be in string. Okay, after that, that particular string is then converted to symbolic mathematics using the simplify function. After which, will then be stored to fx simplify. After that, it will then be evaluated if the function that you entered, or the function entered by the user, is valid. If it is valid, then the loop will be terminated. Otherwise, the system would print invalid equation. Please enter a valid equation. If there are no problems, then the system would proceed to the next step of your process. In this part, the system would ask the user to enter the lower and upper limits respectively. Okay, following this kind of format, we have the x lower and the x upper separated by a space. And then I separated it using the split command so that the individual data will be stored to the individual variables, which is the lower and the upper. If there are no errors again for the inputs, if you inputted a valid limits, then the loop will be terminated. Otherwise, if you inputted, for example, special characters, or you inputted letters, okay, so those are invalid inputs. So the system would print invalid input and then would ask again the user to input again. There are no errors, then the loop will be terminated, and then we proceed to the next process, which is to input the number of segments. Okay, the number of segments should then be evaluated. Okay, it will then be evaluated. If the number of segments is less than 0, then that means that it is an invalid number of segments. Or if it is equal to 0, it is then also be an invalid. So the only valid segments are positive numbers that is divisible by 3. Why? Because this is Simpsons 3/8 rule, and then the minimum number of segments should be 3. And then the next possible number of segments should be divisible by 3. That's why I check if the segments inputted by the user is divisible by 3. Otherwise, the system would print an invalid input, and then we'll continue to ask for another input again. There are no errors, then the system would break the loop and then proceed to the next part of your program. Here in this part, the h is being solved using the formula upper minus lower limits divided by the number of segments. So this would be the step size. Okay. Then, after that is the variables are being initialized. For example, the iteration is being initialized to 0. The xn is initialized to lower, and then the xn1 is initialized to lower plus h. And then the nx2 is nx1 plus h, and so on. And then the table, okay, this is an array initialized so that all the calculated results are then stored to this variable and then further be displayed to the terminal. Okay, after that, okay, this is the loop for the Simpsons 3/8 rule. This is the iteration. Okay, first is, this is a counter, simply a counter for how many iterations has been made. Okay, if the iteration is greater than the segments divided by 3, that means that you have to terminate your loop already. So this is the condition that I use to terminate the loop. Okay, then after that is, okay, you have to get the f of xn. That means that you have to substitute the value of your xn to the function. Then after that, you also have to check for, you also have to get the value of your xn1, and then fxn2, and then fxn3 using the substitution method. And after that, all you need to do is to get the approximation I using the formula 3/8. Okay, that's why this is called the 3/8 Simpsons rule. Okay, multiplied by the h, and then fxn plus 3fxn1 plus 3fxn2 plus fxn3. Then after that, I created a dummy array. Then we stored the necessary values that I will be going to use to display in the table. After that, okay, this would be signified as a row of my table, and it will then be appended to the table. Okay, the dummy array is then be appended to the table. So for the first iteration, it will then store the first row. For the second iteration, it will store the second row, and so on. And after that, a total. Okay, since we want to get the total for the summation of all the approximations, so I stored it in the total. Okay, and then every time it iterates, then it gets, or it gets the summation of all the approximations. After that, this one is to change the values of our xn to be used in the next iteration. And after that, all the data are being stored in the table. Okay, I kind of use the headers so that there is a header in the table. Okay, those are the headers. And then I also get or displayed the Simpsons 3/8 rule approximation rounded to the nearest 5 decimal places. So let's try this one via running this program. You will have to click this code. Let me see. Oh, oops, it's not the Simpsons 3/8 rule. So let me rerun this one. Okay, this is the Simpsons 3/8 rule. Okay, first is will ask for a function. So I already prepared the function. So the function that I am going to use is the same with the exercises. Okay, to check for the validity of my function. So let me check the function first. Okay, this one. You have to enter the function in symbolic mathematics format. And then after that, press enter, and then it will ask you to enter a valid limit. So let's just say in the example I used -2, the lower limit, and the upper limit is 1.6. And after that, press enter, and then it will ask you to enter number of segments. So for example, here in the where is it? This is Simpsons 3.8 rule. Let me check where's the Simpsons 3.8 rule. Okay, this is the Simpsons 3.8 rule. So let's try to use 15 segments. Wait, use 15 segments for this one. Okay, let's try 15 segments. Okay, enter. As you can see, let us verify if the tabulated results are the same. So you can see here, we have, yeah, I think all the datas are the same. And as you can see, the total should be the approximation of the integral using Simpsons 3.8 rule. As you can see, the total is 0.92245, which is actually the same with the table that is shown using the Python code. Okay, so this Python code will now be flexible as to any function that you want. It could accept algebraic functions and also transcendental functions. All you need to do is to provide the limits and also the number of segments. Make sure that the number of segments is divisible by 3 and is also positive. Okay? Okay. So that's it for Simpsons 3 tool. Let's now proceed to the CFDB Richardson extrapolation. This is the code for Richardson's extrapolation, the centered finite divided difference with Richardson extrapolation. Okay. The same libraries are being used, NumPy, SymPy, and Tabulate. Okay. And I also used the symbol x again for all throughout variable. Okay. And then here, these are the declarations of arrays. These arrays are being used in the calculations. And also, this will be the part where you have to save all the datas that are being used. And then, I created two tables. Table 1 is intended for the every stack sizes. And for the table I, this is for the table of improvement. So I will show it later on what are these tables represent. After that is I printed out the header or the title of this method, and which, again, same process. I asked for a function, and then that function is then converted to symbolic mathematics using Simplify. And if there are errors in the functions or the validity of the functions, then it will break the loop. If there are errors, then it will ask again for another input from the user. While printing an invalid equation, please enter a valid equation. Okay, and then after that, it will ask for the value of x. Okay, this value of x is then the part where you, so for example, you want to get the derivative of a certain function at x is equal to this value. So this would be the value of your x. Okay, and after that is, if there are no errors, then it will break the loop, just break the loop. If there are any, then print that invalid input and would ask again the user to input another value of x. Okay, the value of x here is considered to be float. So you can enter an integer value or you can also input the floating point value for x. And after that is you have to enter all the step sizes that you want to perform in the uh, in the in the method. Okay? So all you need to do is to separate those step sizes with space. Okay, so you can enter as many as you want as long as it is valid and is separated by space. Okay? Then I separate those values, individual values, and then stored to the step size array. Okay? Converted, since this is string data type, so I converted it, data casting, to float data type, since you may input the step size with floating decimal numbers. Okay? And after that, again, if there are no errors, then the loop will terminate. If there are any, then would print invalid input and would ask the user to input another step sizes. Now, here is the part where the magic begins. Okay, this is the part where you calculate the individual iterations or individual step sizes. Right? Okay. First is you have to get, right? You have to get the xi minus 1. Since your xi is the initial value of your x, then you have to get the xi minus 1. Okay, the formula should be the initial value of your x minus the step size. And after that is you also have to get the xi minus 2. For that one is you have to use xi minus 1 minus the step size. And for plus 1, this should be addition. And for plus 2, this should be also addition. And to get the value of the function using xi minus 1 as your value of your x, then all you need to do is to substitute the value of your xi minus 1 to the fx simplify, which is your equation or the user inputted equation. And also the xi minus 2, xi plus 1, and xi plus 2. Same process. So this is just a substitution method to get the value of the function. And after that one is you have to get the first derivative. Okay, this is the first derivative of the truncated version of the first derivative using the formula. Okay, as you can see here, this is fxi plus 1 minus fxi minus 1 divided by these two step sizes. And that truncated versions then be saved to f prime truncated. And after that, a more accurate version is then be solved using this formula. This is discussed in the tutorial. Just follow that one. And then after that, I created another dummy array. This will represent the row of each table. Okay, so each step sizes, we get the individual values of the important variables in the code, and then those values are then be appended to the table. After that, if the loop is already finished calculating all the step sizes, then the loop will terminate and proceed to printing out the table for the standard finite divided difference, okay, with the following headers. And okay, this is just the num alignment to write. Okay, another way is the Richardson extrapolation is, since we have a truncated version of the f prime of x, So Richardson extrapolation is simply a method of improving the value of the approximate, right? So that method will then be used if we already have um, uh, two approximations of the derivative. So for example, if you already get the approximation for uh, the step size one, let's just say, and then you also have the value of the approximation using the step size two, and then you have two different approximation using different step sizes, then you can improve that one using Richardson extrapolation. That's why, as you can see here, um, I did not start if my value is if um I have a single step size. I did not start with that one because I don't have a step size to compare with. So I started using the improvement once the I is not equal to 0. That means that the step size has already two step sizes. Okay. Then I use the formula given, which is the 4/3 f prime truncated minus 1/3 f prime truncated minus 1, or the previous. More accurate. This is the more accurate um, approximation. Then minus 1/3 of the less accurate approximation, and then that will be appended again, or being stored to the dummy array. And after that, I rounded up the value to 5 decimal places. And then all those values are then restored to the KPI. Okay. So this is the table for the improvement of the truncated version of the CFDD. Okay, so the method is the Richardson extrapolation. And then it will then be displayed using the tabulate function. Okay, so let's try that one. Let's run it. And okay, this is not the CFDD. So let me just close this one first. Okay, we have, where's the CFDD, Richardson extrapolation. Let's run it. Okay, so this is okay, first is you have to enter the function. So again, I use the example in the exercise. Now I use the equation being used in the exercises for module 2 for me to have a fast verification of the solution for the method that I used. Okay, so again, you have to follow the correct format for the symbolic mathematics of your equation. And after that one, you have to enter the value of your x. So as in the example, let me check. I think it's number 7. Okay. So in this example, centered finite divided difference, the x is 0.75. Let's just input that one. 0.75. And after that one, you need to enter the step sizes. For this example, in the exercise, there are 3 step sizes. So you have to enter the 3 step sizes separated by comma. So first one is 0.125. Second one is 0.0625. And oh, there are 3 step sizes. Okay. The last is 0.03125. And if you enter the step sizes, please enter key. Okay. It will then display the center finite divided difference table. So let's check. This is the forward divided. This is the backward divided. This is the center divided difference. So let's check if all the datas are the same with the manual calculated. Okay. Okay. Let's check the truncated version and the accurate version if it is the same. So we have this one, 0 point, ayan. Yeah, those are, okay. This is more accurate since I guess this is um being rounded up to the nearest 4 decimal places. Okay, this one is not rounded up yet. Okay, this is the more accurate version. Okay, I guess everything is the same. Okay. And after that one, since this is the truncated version, so using Richardson extrapolation, we can improve the approximate of the method. Okay, so it will then be displayed in this table. As you can see, this is just the same as this one, truncated version. And then this is the improvement using the Richardson extrapolation. As H is 0.125, okay, the first step size, I cannot compare it with other step sizes yet since this is just the first step size. So for Richardson to work, you have to use two step sizes. So that's why, okay, I don't have the improvement for this one. So but I do have the improvement for the second one. So these two step sizes are then be compared. Okay, so this one is the improvement. And for this one, okay, these two step sizes are being used. This is the improvement. So let's check if the improvement version is then closer. Okay, I guess, yes, it is then closer to the exact value of the um, derivative of this function. And I guess that would be all for my machine problem. We hope that everything is clear and everything works fine. Thank you so much and have a great day. Bye bye. Thank you.